Okay, this is the first video lecture for Math 181, Calculus 1. And the idea behind these video lectures is I will be posting them to my YouTube channel at least a day prior to the class time. And the idea is for you guys to look at the lectures before class, and then we'll come together during class time via Google Hangout or Meetup, and we can discuss the topic that was covered in the video lecture together. I can do more practice problems, and we can go over homework problems. Okay, that's the idea. This video lecture is for Friday, April 3rd, and we're now getting into chapter 4, which has to do with applications of differentiation. And the idea behind this video lecture is we're going to talk specifically about how do you find the maximum and minimum values for a function. So how do you find those max and minimum values? Okay, let me write that in the board. That's our topic. Maximum, minimum values. Okay, maximum, minimum values. So we given some function. We're interested in finding out the values of x which make that function a maximum value and a minimum value. We're also interested in finding out the values, the actual maximum and minimum values of the function. Okay, but before we get into some example problems, I want to discuss with you guys the difference between local versus global maximum and minimum values. Local versus global. And to illustrate this, I want to show you guys, in Desmos, I've graphed a function here. You can see it over there. It's 2x to the fourth minus 4x cubed plus 3x. Now this function clearly has a minimum value here at that value. Okay, and it has a maximum value here and a minimum value here. But these maximum and minima are not all the same. This minimum is called a global or absolute minimum because it's the absolute minimum value of this function. It's the smallest this function will ever become. Okay. This maximum, though, is called a local maximum because for values near this for values of x near this point right here, this is a maximum. But if you go over to here or to here on the wings, the function becomes larger than the maximum value here. So this is only a maximum over a very small interval near the maximum value of x. So we refer to this as a local maximum. This point here is referred to as a local minimum because for values of x near this point, this is a minimum value. But if you go down to here, the function becomes smaller than this value. So this is not an absolute minimum, it's a local minimum. It's only valid for values of x near the minimum. So that's the basic difference between local and absolute maxima and minima. So just be careful when you're doing a problem to distinguish those two. Okay, we're going back to the board. Okay, what I want to do now is I want to talk about how do we find local maxima and minima. So finding local maxima and minima. How do we find local maxima and minima? Well, we use something called Fermat's theorem. Okay. And this says that if we have a local maxima and minima, for some function x or f, for some function f, okay, and f prime of c exists, then f prime of c equals 0. So what this says is, if we have a local maximum or minimum value of a function at a particular value of x, and the derivative of that function at that value of x exists, then the derivative of the function at that particular value equals 0. Okay? So let me talk about this. This might seem like it's complicated. It's pretty simple and straightforward. Let's look at this function here. If you look at this minimum, right, the derivative is the slope. Well, what's the slope of the function at this minimum? The slope of the tangent line to this function is 0. So the slope is 0 at this, so we have actually a global minimum and the slope is 0 here. We have a local maximum, the slope is 0 here. We have a local minimum, the slope is 0 here. So anywhere you have a local or global maxima or minima, the slope is 0 as long as the function exists. Okay. Couple words of caution about this. Couple words of caution. Okay, there's two things I want to caution you guys about. Let's consider the function f of x equals x cubed. Okay. This function very roughly looks like this. This theorem does not go the other way. If you have a place where the derivative of the function is 0, it doesn't necessarily mean you have a local maxima or minima. In particular, the slope of x cubed at x equals 0 is 0. So the slope is 0, but we don't have a local maxima or minima. We just have a little temporary plateau. So you can't go the other way with this theorem. And the other word of caution I would give you is in regards to this function. As an example, the absolute value of x. If we graph this function, we get our classic V shape. This has a global minimum at x equals 0. Okay, but we have a kink in the slope of this. So although we have a global minimum here, f prime of 0 does not exist for this function. So therefore f prime of 0 does not equal 0. So just because you have a local maxima or minima doesn't necessarily mean the derivative is 0 if the derivative doesn't exist. So the derivative has to exist at your local maxima or minima. So two words of caution. Okay, let's talk about critical numbers. What are critical numbers? These are numbers for which f prime equals 0. They're often referred to as C. They're often indicated with the letter C. So these are basically the values of x for which the derivative of a function is equal to 0. Those are your critical numbers. When you're given a function, you often, first thing you do is you'll want to find the critical numbers, find the values of x for which the slope of the function equals 0. Let's do an example here of this. So I'm going to do a couple examples. Here's one example. Let's find the local maxima and minima of this function f of x equals x cubed plus 6x squared minus 15x. Here's our example. We want to find the local maxima and minima of this function. Okay, how do we do that? So this is the meat of today's lecture. How do we find the maxima and minima of a function? Well, what we do is we take the derivative of this function. Okay, in other words, we find the slope of this function. Take the derivative, we get 3x squared plus 12x minus 15. Okay, and then what we do is we set this equal to 0. All right. Why 0? Because we're trying to find the places for which this function has a 0 derivative. Because usually, if it's well behaved, then those are the places where it has a local maxima or minima. Okay. So what we do is we take the derivative of this function, set it equal to 0. Okay, and we find the values of x that make it 0. And those are the critical numbers for this function. Those are the numbers for which it typically will have a local maxima or minima. Okay, so let's solve this for those values of x. I'm going to factor out a 3. We get x squared plus 4x minus 5 equals 0. The 3 goes away. And then we get this equation. We can factor it further, and we get x minus x plus 5 times x minus 1 is how this equation factors. We then solve for x, so we get x equals 1 and x equals minus 5. Okay. Those are the critical numbers for this function. These are the numbers for which the derivative of this function is equal to 0. Okay, and then what we'd like to do is we'd like to find out what are the various values of this function at those numbers. So we can plug in f of 1. Okay, f of 1 simply equals 1 plus 6 minus 15. Okay, plugging in x equals 1. And that gives us minus 8. And then we can also plug in f of minus 5. I'll spare you guys the arithmetic on this, but it comes out to 100. So we can actually figure out what we're dealing with. This is actually a local maxima, and this is a local minimum. Okay, so that's the classic problem. Find the critical numbers of this function, find the maximum minimum values of the function at those critical numbers. Let's log into my computer here, and we will graph this function. So you guys see how it works. Okay, I'm going to graph this function here. Just give me a second. This is x cubed minus plus 6x squared. Oops, got a little bit crazy there. Plus 6x squared minus 15x. Okay, let's go over to our camera here. Let's zoom out. Okay, and we can see that indeed our function has a local maximum, a value of 100, a local minimum value of approximately minus 8. If we zoomed in, we'd see it's minus 8. And we see this minus 8 value occurs at x equals 1. And this maximum value, if we can zoom up there, the maximum value, I'm too close to the screen here, occurs at 100. So in fact, what we found here is in fact what's borne out by this graph. Okay, let's do another example problem. Instead of there's a procedure for finding an absolute max. So there's one more topic we need to talk about. It's finding a global max or minima on an interval. Okay, finding a global max or minima on an interval. And there's a method we can use. So we can find, this method involves finding values of f at critical numbers and then we also finding the values of f at the endpoints of the interval. Okay, so this method, suppose you have some function and you want to find the global maxima or minima of that function on some interval. Here's the method we can use. What we do is we find the critical numbers of the function. We find the values of the function at those critical numbers, and we find the values of the function at the endpoints of the interval, and we compare these two. And so we compare 1 and 2. So to find a global maximum, we compare the values of f at the critical numbers and the value at the endpoints, and whichever is bigger is your global maxima. To find the global minimum, you compare the values of the function at the critical numbers and the values of the function at the endpoints, whichever is smaller is your global minimum. Now, if this doesn't make any sense to you, it will in a second, because we'll do an example. So this is the final example for today. This is the procedure, but I think an example will illustrate this a lot better. So we're going to do this example here. We have this function, f of x, equals 5 plus 54x minus 2x cubed. And we're considering the interval 0, 4 inclusive. So suppose we have some function, and we have a certain interval, and we want to find what are the maximum minimum values of the function on this interval. Let's think about this. Let's try to let's try to find the values here. df, we're going to take the derivative of x, okay? Derivative of, the function here. So what happens is we get 54 minus 6x, okay? And then what we do is we set this equal to 0. So what we're doing is we're finding our critical numbers here. So it's another critical number example. We solve for x. This means 6x equals 54. Okay, this means x equals, x squared. 6x squared equals 54. X squared equals 9. That means x equals plus or minus 3. So apparently the critical numbers of this function are plus or minus 3. Okay, but only one of these numbers is on our interval. Only 3 is on our interval. So that's all we need to really care about here. What we're going to do is we're going to find the value of our function at f equals 3. Okay? And I'll save you guys the arithmetic of doing that. But if you do that, the value of the function at f equals 3 is 113. Okay? And then what we do is we find the value of our function at the endpoints of this interval. So the value of the function at f is 0. What is that equal to? It looks like it's 5, correct? Yes. And then the value of the function at the other endpoint, f equals 4. I'll save you guys the arithmetic of that. That comes out to 93. 93, okay. So, this is interesting. So what we can conclude here is that, what do we have here? It looks like we have a maximum occurring. We have on this interval, so on this interval, we have, probably a better term is absolute than global. I like absolute is better. This is not global to the whole function for all x. This is an absolute maximum minimum on the interval. So what I can conclude here is that the absolute maximum on this interval is 113 occurs at x equals 3. Okay, because this value is bigger than either of the endpoints. And we know this is a local maximum. And then the local minimum occurs at x equals 0 of 5. So that the local minimum occurs at the lower endpoint of this interval. The local the absolute minimum on this interval occurs at x equals 0. The absolute maximum occurs at x equals 3. Okay, and so we found our absolute maximum minimum on this interval. The last thing I want to do is I want to just show you guys the graph of this. Let's just see if this is true. So we have our handy Desmos program. Let's do this. By the way, if I'm talking fast, the reason is I'm trying to make these videos as short as possible because the upload times are really significant. And you guys can always, the nice thing about these videos is you can always pause them or replay them if something doesn't make sense. So what I'm going to do is I'm going to graph this function, which is 5 plus x, 54x, minus 2x raised to the third power. Okay, this is what we get. Let's look at this function. I'd like to spread out the x and y axes, but anyway, this is what we'll do. Let me see if I can do that. Probably not. X-axis doesn't need to be so big. Let me just do this. Let's go like minus 40 to 40. Okay, just hold on a second. This thing is not letting me do this. Minus 40 to 40. Okay, that's a lot better. Okay, and I'm going to bring this camera over. Okay, so if we zoom in here, we're considering the interval from 0 to 4, which is this interval from 0 to 4, okay? We see that on this interval from 0 to 4, we have a maximum value of 100, looks like it's 113. And that occurs at it looks like it occurs at x, not approximately, at x equals 3. And then on this interval, the global minimum on this 0 to 4 occurs right at the edge of the interval at x equals 0. And it looks like the function's value at x equals 0 is 5. So that's cool. That concludes our lecture. Anyway, I'll see you guys at class time on Friday. Thank you.